In this video, we're going to start the proof that the set of Gaussian integers forms a Euclidean domain. In order to get started, I want to do some basic review of the things that we need to know before we can start the proof. First of all, the Gaussian integers are defined to be the set of a plus bi's, where a and b are pulled from the integers. I is the square root of -1, and so that means that the set of Gaussian integers is a subset of the complex numbers. The next thing is in a previous video, we have shown that the Gaussian integers forms a subring of the complex numbers, and it's important to remember that the complex numbers are a field, and hence there are no zero divisors inside the complex numbers, and that means that the Gaussian integers have no zero divisors, and that says that the Gaussian integers are in fact an integral domain. And what this means is that to show that the Gaussian integers are a Euclidean domain, all we need to do is we need to find a Euclidean valuation on the set of Gaussian integers. Now, Euclidean valuation is a tricky definition, so I actually want to review that as well before we start on our formal proof. When we say that nu is a Euclidean valuation on a domain D, what that means is that, first of all, nu is a function from D to the set of non-negative integers, and it has to have two properties. And the first property is that if a and b are non-zero elements of my domain, then nu of their product has to be bigger than or equal to nu of either of the factors. So nu of AB has to be bigger than nu of A, and it also follows that nu of AB will also be bigger than or equal to nu of B. And the second property is that if I have any two elements inside my domain, A and B, and B is known to not be zero, then I can find R and Q inside D such that A is equal to Q times B plus R, and significantly, nu of R has to be strictly less than nu of B, or R has to be the zero inside my domain. This basically says R is somehow smaller than B if B is not dividing A. And I want to kind of put that in context with the complex numbers. So first of all, we have to find a candidate. So we need to find a candidate for nu going from the set of complex integer, either the set of Gaussian integers, to the set of non-negative integers that will work. Well, I want to be thinking in terms of size inside the complex numbers means the modulus of a complex number. And if I'm thinking in terms of the complex plane, so this is my real axis and this is my imaginary axis, if this is the number a plus bi, the distance between 0 and a plus bi is defined to be the modulus of this guy, and that's known to be a squared plus b squared underneath a square root sign. Now the problem is that if I let z be a Gaussian integer, so z is equal to a plus bi, where a and b are known to be integers, then yes, I can define the modulus of z to be this particular number, but in general, that number is not inside the set of integers. And so the norm or the modulus is not going to work. But what I can think of is that if I square that norm, I'm going to get a squared plus b squared, and a squared plus b squared will be a non-negative integer. So this will be an element of in union the set containing 0, the set of non-negative integers. So it turns out that this particular thing is a good candidate for our nu. So we are going to define nu going from the Gaussian integers to the set of non-negative integers by nu of a plus bi will be a squared plus b squared. And the question now is nu a Euclidean valuation on our set of Gaussian integers? Now that means we have to verify both properties. Well, let's look at the first property. Does nu satisfy property 1? In other words, if x and y are inside the Gaussian integers and they are both not 0, is nu of their product bigger than or equal to nu of one of the factors? And it doesn't really matter which factor, so I'm just going to worry about x. Now, to look at this, we're going to actually have to set up some notation. We will let x be a plus bi, and we will let y be c plus di. Now, because I know that x and y are not 0, that says at least one of a and b is not 0, at least one of c and d is not 0, and what I want to note is that that says that the value of nu of x, which is a squared plus b squared, is not going to be 0, and the value of nu of y, which is c squared plus d squared, is also not going to be 0. In other words, I do know that nu of x is at least as big as 1, and nu of y is also at least as big as 1, because they are sums of squares of integers. Well, let's see. We can also figure out what x times y is. So x times y is a plus bi times c plus di, and this is going to be ac minus bd for the real part, and then we are going to have ad plus bc times I for the imaginary part. And what I now want to do is I want to look at nu of x times y. Well, that's going to be ac plus bd, not plus, ac minus bd, quantity squared, and I still have a straight arc there, plus ad plus bc, quantity squared. And when we square this out, we're going to get a squared c squared minus 2abcds plus b squared d squared. And then when we square this term, we're going to get plus a squared d squared plus 2abcds plus a b squared times a c squared. And when we start looking at this, we notice that this guy and this guy add together and form a 0. And so what we're left with at this point is a squared c squared plus b squared d squared plus a squared d squared plus b squared c squared. And what I want to do is I want to do some partial factoring. So I'm going to rewrite this in the following way. We're going to gather up the two terms that have a squared in them. We've got a squared c squared plus a squared d squared. And then we've got b squared d squared plus b squared c squared. And when we do the factoring, we can easily see that out of this part we get an a squared that factors. So we have a squared times c squared plus d squared. And over here we've got b squared times d squared plus c squared. Of course, c squared plus d squared and d squared plus c squared are the same thing. So we can factor again and we get a squared plus b squared times c squared plus d squared. But as we just saw a few minutes ago, and I want to kind of recall this, we know that a squared plus b squared has to be at least as big as 1 because one of a and b is not equal to 0. And c squared plus d squared is also at least as big as 1 because at least one of c and d is not 0, and a, b, c, and d are all integers. And so what we have here, recall that this is nu of xy. This says nu of xy, of x times y there, is equal to nu of x times nu of y, and this guy here is bigger than or equal to 1, so the whole thing is at least as big as nu of x. And what that says is that nu satisfies property 1. We will show that nu satisfies property 2 in a separate video.